welcome to Talk Universe. This is our show for Wednesday, October 26, 2016. Tonight we address an interesting question: is time travel possible? We are all familiar with the science fiction stories about traveling through time, all the interesting things that can happen. But is this a possibility? We've probably all thought about if we could go back and do something over again, what we would change, what we would do differently, what we might bring back in terms of information or even hardware. How would you travel in time? Is it possible at all? What effects would it have? Could we really change history, or are we locked on a track once something has happened that is unchangeable? There have been many questions about the theories of time travel, and there are some indications that it might be possible. But we haven't, so far as we know, seen any actual time travelers. So what does it mean? Maybe they're very good at hiding themselves, or maybe time travel isn't possible at all. We're going to look at some of the possibilities on the show tonight. So what exactly is time travel? We can easily consider the possibility of moving from one point on the map to another. But when we think about moving forward or backward in time, it seems to be a little bit different for us. Exactly what is time, and is it traversable like a map? These are questions that we really have to resolve before we can even begin the thought of building a time machine or traveling in time. Now, anyone can imagine moving north, south, east, or west, or any other conceivable direction on a map or in a building or anything in space. But when we think about moving in time, we generally recognize that there are really only two directions you could move, forward or backward. In a strange sense, we're all traveling in time because the moment of now is moving forward at a consistent rate, and we're being carried along with it almost as if we're on a wave. And imagine a surfboard riding that wave. At least on a surfboard, you can direct your movement right or left. You can speed up or slow down a little sometimes. But in time, what exactly would be the effect of moving sideways? Is such a thing possible at all? First of all, let's consider what time is really like and what it would mean. In periods of time before the 20th century, it was generally not recognized that time wasn't a uniform thing. Most people thought of time as being absolute, unchangeable. And yet, in the period of time leading up to Einstein's work, it was discovered that time, as Einstein proposed, is not flat or uniform or absolute at all. It actually changes depending on your frame of reference or your velocity. So what exactly is velocity? Velocity isn't just your speed, but also a direction. Velocity is speed and a direction taken together. So two vehicles traveling at 60 miles per hour, but one aimed north and one aimed west, have different velocities, even though their speed is the same. So velocity is something more composite in nature than simple speed. And this is a very important thing to understand. The direction you're traveling is a part of your movement. Now, it's possible for your speed to remain constant, but your velocity to change. Just imagine traveling in a circular path at a constant speed. Here your speed is constant. Yes, you stay at 60 miles per hour, for instance, but as your direction is changing, so is your velocity. When you talk about time, it's possible for your speed to change, but your velocity to remain constant. This is because the passage of time is an essential part of the equation. Now, an important discovery is that the passage of time, the rate at which time flows for you, can vary based on where you are. If you're away from a planet, if you're floating in free space, away from any source of gravitation and far from any other mass, time is moving at a regular clip. But when you get near a massive body such as a planet or a star, the rate of your time's passage slows down slightly. And when you're standing on the surface of the Earth, your time actually moves slower than if you were free-floating in space above the Earth. But the amount of change is incredibly small, in millionths or billionths of a second. There's also another effect where the faster you travel, the slower your time will flow. So if somebody were to be standing by as you traveled around them at thousands of miles per hour in a circle, and then you came to a stop, you would find that you hadn't aged quite as much as your friend standing still on the ground. This effect was put to the test many years ago by buying 2 tickets on an airliner where a fellow carried an atomic clock in the seat next to him. At the end of the flight, his atomic clock had actually run slower than the atomic clock on the ground, and the predicted amount of time dilation or shift in time flow was exactly measured. So if you were capable of traveling at extremely high speeds, like near the speed of light, you could actually slow the passage of your time down significantly. And on a long trip through space, traveling near the speed of light, you might spend what appears to you to be a month or two traveling on your spacecraft, but upon returning to the Earth you might find that a century had passed. Now, this could be a very unsatisfactory form of time travel, which only allows you to move into the future. However, you could actually move dozens of years, centuries, or millennia with ease if you could reach speeds near the speed of light. And in fact, this is done routinely in particle accelerators. There are many atomic particles or nuclear particles that break down in extremely short periods of time. Scientists who wish to study these particles know that there's not much time to take any readings. So how do they get around it? By boosting those particles to extremely high velocities, they can literally slow down time for those particles and stretch their lifespans out hundreds or thousands of times longer than they normally would live. This is an effect of time dilation, the same sort of time travel if you were to move very, very rapidly. But again, it's limited to only moving into the future and not backwards in time. And a lot of times when we speak of time travel, we imply that we'd like to go back to the past to observe or interact with things. So is that at all possible? Well, we do know that the fabric of space-time is stretchy, and that certain events or certain conditions can create periods of time that move much more slowly or even stand still. But can they reverse time? Some physics suggest that it's possible, but we're not exactly sure just yet. Now, we can easily calculate that if you were to stand on the surface of a neutron star without it killing you, that the movement of time for you would only be about 88% as fast as it would be for somebody observing you from a distance. And we also can tell that if you were able to orbit a black hole at fairly close range, just above the area where it becomes truly dark, then your time could run slower and slower as you orbit the hole until the point where it would absolutely stand still. But at that point, you'd be doomed. You couldn't get back out again. But your time would be standing still from the standpoint of an outside observer. Now, obviously, any time machine that we could build or use would have to be a lot friendlier than a neutron star or a black hole. So we'd need something a lot more compact. Furthermore, we would also want the ability to travel backwards in time. So is it possible? We surely can travel forwards in time, but backwards, that's another challenge entirely. So let's start over and think about the possibilities of time travel at all, and what the simplest methods are, and which ones are practical and which ones are not. Let's start with the simplest method, one that only works forward in time and something we could achieve today, and that would be cryogenically being frozen. Now, if you could do this and not be killed in the process and then resurrected later, you could effectively sleep for a year, 10 years, 1,000 years, and wake up at that point in the future, and your experience would be you'd taken a brief nap. This isn't a time machine at all, but it can act like one, and it's only one directional. Of course, in science fiction, the equivalent is called the stasis field, the theoretical idea that somehow you could stop time in a volume, and anything contained within that volume would be absolutely static until you turned it off. Such an idea isn't outlandish. If we could find some way to manipulate the speed of light in a volume, then yes, we could have a stasis field, something that would be utterly time-free and stopped until you deactivate it. And so this acts like a time machine that runs into the future. But it has other applications as well, which I won't go into here just yet. Next, we have the relativistic velocity method, which I spoke about earlier. The faster you move, the slower your time moves. And if we could take something to a point where it had no mass at all, we could accelerate it to the speed of light, and there, anything suspended within that object would be time-free for whatever period of time it remained in that state. But in order to make that method useful, we would have to learn how to remove the mass from an object, or at least temporarily do it. Now we get down to hypermasses, something with the mass of a star or much more mass concentrated in a small space. And if you were close enough to it, your time would slow down. Or if you were in orbit around it, your time would slow down, because if you could orbit very close to the speed of light around such a thing, then you would effectively have reached the relativistic velocity type time slowdown or time travel. But again, this is only forward time travel and a little disappointing in some respects. So let's talk about other methods. Now we come to something a little odd called the Tipler cylinder. Let's imagine you had a long cylinder, in fact, infinitely long cylinder, made of a black hole material or a rotating neutron star, a hypermass. If it were spinning rapidly enough and you were to fly around it, theory suggests that you might be able to travel backwards in time. Now, actually, Tipler felt that this thing could have been made a lot more compact, not infinitely long, but still incredibly massive and quite long. And this is not something that we can build. We can't even do anything with a star, much less make something out of a black hole or a neutron star. But it does seem to illustrate that it might be possible to make a time machine using a rotating, elongated mass. And we'll get back to that very shortly. Frank Tipler was actually quite deeply into relativity and physics and felt that this might be a solution And that brings us to the possibility of other methods of stabilizing it or making it work. Stephen Hawking, on the other hand, feels that it won't work without the presence of something called negative energy. He feels that this can be proven not to work because of the lack of negative energy or exotic matter, and we won't even touch on that just yet. But if you had the sort of technology necessary to shape a black hole or a number of black holes into specific shapes or structures, then you might be able to take the Tipler cylinder and do something a little different, wrap it around itself in a donut. So now you have a toroid, or a donut, and this toroid would spin so that it was going through its own hole over and over again. Now, in this case, you end up with an exotic structure that has to rotate in two directions at once. One with the ring spinning like a frisbee around its own axis, and the other where it's falling into the hole on the other axis, like going down the drain over and over again. This sort of structure, if made of a black hole, could be spun to hold the hole outward so it couldn't collapse inward on itself and close, and it would be spinning toward its own center over and over, and this would provide the twisted space-time necessary to travel forward and backward. You simply would go through the hole in one direction or the other to go into the past or the future. But all this engineering takes abilities way, way beyond what we as human beings are capable of, and there must be a simpler way to do it, and maybe there is. This is where we step into the world of wormholes. Everybody knows what a wormhole is. It's a hole through space-time that has an entrance at one point and an exit at the other. And when you go through a wormhole, the idea is it should take you through a shorter path to reach some distant point. Now, while we don't know how to create a wormhole just yet, there are some ideas. And it would also require exotic matter, something which is completely different from normal matter. But if we could create a wormhole, then we do have the possibility of making a time machine in a very interesting manner. And it follows using the same method as speeding things up to slow their passage of time. Let me explain this. A wormhole always has at least two ends, an entry and an exit. And if you were to take one of those ends and leave it here at home and put the other one in a fast spaceship or a particle accelerator and shoot it near the speed of light, then it would stop aging. Now, the stay-at-home end would age at the normal rate, but the other end, having moved very, very rapidly, would be essentially anchored at some point in the past. Now, this has an interesting effect. If you were to enter one end of that wormhole, you'd end up at some time in the future. But if you were to go through the other way, you'd end up at some time in the past. Let's imagine that that distance in time would be 1 hour. Now you have a wormhole that traverses forward or backward 1 hour in a step. This is definitely a time machine, but in all respects it's more like a time tunnel or doorway. And when you step through it, you can only go as far as the wormhole was created, backwards in time, and as far forward in time as the wormhole would continue to exist. So it's really more like an overpass on a highway than an actual movable time machine. Now, as some people point out, if we could make a warp drive or something like the Alcubierre drive, which has been theorized recently, if we could move faster than light, we also could have time travel. Because you see, moving faster than light means that you can get information or objects somewhere faster than light itself, which means in many cases you could get back to an event before it actually occurred. But from what we understand, we still would have to use negative energy or exotic matter to make this sort of drive work. And I'll talk about that in a little bit. It's something that's very difficult to wrap your head around, unless you understand a bit of physics, however. Now we come to a method that I came up with one evening when I was thinking about different ideas in time travel. And it's an idea where you actually use entanglement and quantum effects to recreate a state of the past, feed it into an incredibly detailed computer simulation, and then you step in like virtual reality and use the computer space to simulate time travel to any previous time. This is actually something that we might be able to do to some degree now, and with real fidelity later when we get a better handle on quantum mechanical effects and how they work. Now, while this idea is not actually time travel, it's connected to it in a funny sense. Scientists have recently created something known as a time crystal, which is a structure that is crystalline in nature but extends through the fourth dimension. There's an information portion of the crystal that extends through the fourth dimension through time and sustains itself in the crystal indefinitely. Whether this can actually lead to real time travel or even sending information in time is unknown, but it's certainly something worth investigating. And what about that idea, sending information through time? It might be just as good as sending real solid objects. This is Talk Universe. One of the most popular concepts in time travel is that of a paradox. Just imagine the movie Back to the Future. What would have happened if Marty had stepped into the DeLorean, traveled back in time, and when he emerged, he had run over Doc Brown before he had actually built the time machine, and he was killed? What would happen to Marty? You see, this is a paradox. If Marty had run over the Doc before the first time machine had been invented, then there wouldn't be a time machine for Marty to be in the first place, and it could never have taken place. So a paradox is when a set of conditions occurs that may actually prevent their own occurrence. This is a common theme in time travel. Somebody goes back in time, shoots their own grandfather, and then they don't exist. There are a lot of thoughts about what might happen if you could actually do this. One is that the event could never occur, and so it would self-present itself. Time would be consistent. But quantum mechanics is a strange thing, and there's something called the Copenhagen interpretation, or the many worlds interpretation, which suggests for every decision we make, the universe might split and go in two directions, whether you chose yes or whether you chose no. If this is true, there would be an infinite number of universes very similar to our own, but with minor differences here and there throughout their structure. And one of them would be, you went for a donut, you didn't go for a donut. It seems rather trivial, but in some cases it seems to follow the rules of quantum mechanics. If this were true, then traveling back in time and creating a paradox would make the universe split off in a different direction, and you'd end up in a universe almost as an orphan, with no genesis for yourself. You would come from another universe and end up in this universe that was different from the one that you had originally lived in. This is not so unbelievable also. But the more you think about it, the more it seems that time travel would force consistency, because otherwise any time machine could become a device for creating an infinite number of universes from the smallest decision. Paradoxes aren't the only thing you have to worry about if you're a time traveler. One of the things you have to worry about is this. The Earth is in motion. It's orbiting the sun. And if you were to jump in a time machine and go back 15 minutes in time, or forward 15 minutes in time, you would find that you were completely off the surface of the Earth by about the width of the planet, or over 8,000 miles. This is because in 14 minutes, the Earth completely crosses a distance of space equal to its own diameter. So if you were to jump in a machine, go back a minute in time, you might find yourself buried deep inside the Earth or free-floating in space, not on the surface of the Earth. Because what's the guarantee that the time machine will be moving to exactly the same spot that the Earth will have been at that period of time that you traveled to? Almost none. But there's another concern, and it's similar to that. Suppose you did travel in time and you arrived exactly where you expected. Now, obviously, if somebody was walking through that space or a solid object were there, or maybe you were off a few feet and you ended up in the side of a building, it would be disastrous. Obviously, two objects can't occupy the same space at the same time. And if you're coming through as a time traveler, you're probably entering from the fourth dimension linearly, and nothing would stop you from colliding with an object. But suppose you ended up in atmosphere. Air molecules are matter, and you can't occupy the same space as another object, even if it's a gas. If you were to occupy the same space that air was already in, you would probably explode with more force than an atomic bomb. So what this points out, first and foremost, is that a time machine of the sort that Doc Brown had would have to actually be a time and space travel machine, and it would have to calculate every move in 4 or more dimensions to know exactly how it was going to land and where and when. So it becomes much more complicated than simply stepping back in time. But furthermore, it's only going to be safe if you're traveling in a vacuum, because otherwise you're going to end up occupying the same space as air or water or solids. So time travel of that sort would only be safe if you did it in space, and even then there are no guarantees. So what if we go to the wormhole type time machine, which we actually could possibly make if we knew how to make a wormhole? Well, it has its problems as well, and one of them is this. The wormhole has an event horizon, a boundary layer, if you will, and it's shaped not flat, but like a sphere. It bulges out all around like a ball. Now, if you remember the Terminator movies, they had a ball-like time displacement field. This is actually fairly accurate. You would have a spherical time displacement field for the wormhole mouth. Each end of the wormhole would have one of these spheres. But here's the curious part. For anything entering it, The curve is convex. It sticks out toward them. And as you were to step into it, the interior is fairly uniform or curved in a uniform manner. But the space leading up to it is curved differently. Picture a drain in a sink, and imagine laying a flat sheet of paper in the bottom of the sink, and then sliding it up toward the drain and pushing it into the drain without tearing it. It's not going to happen. There will be destruction. The same thing would happen to any material object entering the curved surface of the event horizon of a wormhole. Because the geometry of the event horizon entrance is different from the geometry of the wormhole neck or throat, and again, negative compared to the exit end of the wormhole, there's going to be a lot of destruction for solid objects that enter a wormhole to travel through it, unless we can find a way to create a flat or uniform entry and exit. Now, as you can imagine, if the wormhole were made large enough, then the curvature would be very small or negligible, and this effect wouldn't make much of a difference. But a wormhole of that size is something you're not likely to be able to do on the surface of a planet, which leads us to the possibility that the huge, enormous black hole at the center of our galaxy might be usable as a time machine. Now, some people have proposed this, but it has some issues with it as well. For one thing, it's over 30,000 light years away, and getting there isn't going to be a snap. In order to make use of a time machine at the center of our galaxy, we'd have to do a little bit of logistics here. You would have to travel 30,000 light years. Then you would have to plot a path through the wormhole that would bring you back to the proper point in time. But here's the catch. Now you have to travel 30,000 light years back to the Earth, wherever it is, and you have to find it. Let's say that you could do that. Let's say that your navigation skills were amazing. So you travel 30,000 light years to the wormhole, back in time, let's say, then 30,000 years back to the Earth, and 60,000 years, plus however long you traveled in time, is what you have to take into account. Well, it makes pretty good sense that even if you could travel at the speed of light, you still have 60,000 years to get out of the way, and you have to do it accurately. So let's say you wanted to go back 100 years in time, from 2016 to 1916. Well, here's how it would play out. You would travel at the speed of light for 30,000 years to the center of the galaxy. Then you go back 60,100 years through your wormhole at the black hole at the center of the galaxy. Then you would travel 30,000 light years back home. Now you would be 100 years in the past on Earth, all things being equal. But the amount of enormous overhead required to do it would make it probably very impractical. So even if there is a usable black hole that could send us through time at the center of our galaxy, and there is a black hole there, we just don't know if it actually reaches through time. But even if you could do that, it would be extremely tricky, and you'd have to make 60,000 years of journey through space without hitting something on the way. So it's pretty clear that any civilization that undertook this sort of a journey would not be doing it for something trivial. In fact, it would probably only be done in the case of some planet-wide or solar system-wide disaster or catastrophe that had to be averted. But if this were true, it would also be a pretty good indication that there wasn't a simpler way to do it, that traveling to the center of the galaxy would be the only way that they could pull it off, which wouldn't be a very good indicator for smaller or more compact time machines. But it also seems to me that if you really think about the possibility of a paradox, that time travel, specifically time travel through wormhole-type time machines or through black hole-type time machines, would probably mean that if those pathways were already connected, that quantum mechanics would somehow resolve the two so that no paradoxes could possibly exist, sort of like setting the rules over the entire sheet of graph paper. Now, if this is true, then we don't have to worry about paradoxes at all. And if you come to think about it, that makes a lot of sense. The universe is still going to be consistent. After all, if you're using a wormhole or black hole type time machine, or a Tipler time machine, or a ring, and you go back in time, you can only go back to the moment when the thing was created. You can't go back previously and prevent it from being created because it didn't exist then, so there's no way for you to go that far back. It's kind of like the length of a bridge. You can only travel on the bridge from one end to the other. You can't keep going past the end of the bridge and still be on the bridge. But with all of this being said, there's one method of time travel that I haven't mentioned yet that might actually be possible and involves wormholes, but only extremely tiny ones, quantum wormholes.
You see, the smaller a structure is, the more undetermined its space-time waveform is. In other words, because of something known as the uncertainty principle, it's possible for extremely tiny particles to move all around in space and possibly even forward and backward in time slightly. The effect would be extremely, extremely tiny. Smaller than a billionth of a second, smaller than a trillionth of a second. The effect would be so tiny that it would be about 43 orders of magnitude smaller than 1 second. Now, on the order of this scale, it's possible for particles to tunnel backwards in time. And if you could create a wormhole that was as small as the tiniest particle, and you could anchor it so that it moved further and further backward in time, tunneling slight fractions of a second each moment it existed, it's possible it could be forced to move backwards in time to some significant distance. Now all you need is the ability to steer it wherever it needs to be, and it would be very helpful if you could allow information to come through the little wormhole so you can see where it was. This sort of system is almost like an endoscope being moved in somebody's body for surgery, but instead, at the tip of this thing is a tiny wormhole that allows you to send and receive information. There would be some difficulties working with this, of course, because if it were large enough to send and receive information through, it would be too large to perform this quantum tunneling. But if it were small enough to tunnel, you couldn't be absolutely certain where you were steering it. So you would have to drive it for a while as far as you could, open it up a little and take a reading. And then you'd have to collapse it to a point again, move it back a little more, and open it up again. This would be a slow and tedious process getting it back to where you wanted it to be and aimed where it should be. But at least it's something that might be workable. And when you open it up, it would be large enough to pass maybe some gamma radiation through it. Now that doesn't sound very impressive, but if you can send and receive gamma rays, they're just as good as binary information, and this is the same way that computers communicate. So you'd have a device which you could send back to some point in time and space, and then you could look through it and see what was going on. Once you got it where you wanted it to be, you'd open it up enough to actually get light waves through it, then you could observe and possibly even listen to what's going on in the surroundings. This might not sound like much, but if you think about it, that information could be projected in a room or used with a quantum computing system to create a simulation of the past that you could actually interact with. And yes, this information would be from the past. Could you send information through the other way? Quite possibly. Once you have the wormhole in place, then it becomes simply a matter of mechanics. Now, this idea is possible, and if it's possible, then maybe somebody in the future has already done it, which would mean that we might have to look around us for miniature, exotic points of energy or density that we couldn't explain. If we could find quantum wormholes around us in our environment, then we would know that it's quite possible somebody in the future could be listening in and watching. And it could also explain why we don't see time travelers, and we haven't seen any, because maybe they're simply looking in or using methods that we wouldn't use or think of. So at this very moment, scattered throughout history, there could be tiny quantum wormholes peering in, listening and seeing everything that's going on and recording it for posterity. Everything we think we know, every event, every person, every place could be recorded in great fidelity right now at some future time. And we would be unable to detect it unless we had the ability to detect these tiny quantum wormholes. How would we go about doing that? Maybe we'd look for distortions in gravity, or mass that shouldn't be present, or some other anomalies such as tiny bursts of X-rays or radiation we couldn't explain. In any event, it's quite possible that future technologies that we haven't thought of are in use right now, and that the past, which would be us, could be under observation. This is something that nobody seems to consider, that maybe we don't see time travelers because they're doing things in a way that we haven't actually considered, things that make a lot more sense. So just imagine being able to hear and see everything throughout history and bring it back home to the moment where you live and put it in a huge simulation so that you could interact with, learn from, and do things in the past without actually altering it in any way or posing a threat. This is the sort of technology that we would really expect from people who were smarter and had more technical expertise than we do. This is the sort of thing that the future would present. Imagine all of history open like a book, and anyone you ever wanted to see available. This is Talk Universe.
What kind of world would we have if time travel was known and commonplace? What if we could only send information back and forth from the present to the past to the future? There are a few things that would happen right away, and one of them is this. Economies, if they exist in the future, would be very stable. You would already know what the market would need, where things would go, and how things would change. Therefore, there'd be no wild fluctuations in the prices of things if there were any future stock market. Another advantage would be you would always know of oncoming natural disasters. You would have the time and facilities to prepare for things well in advance. So, people wouldn't be dying in meteor strikes or tsunamis or volcanic eruptions, because you would already know well in advance and be able to get people to safety and make the appropriate plans. A world in which time travel is a part of your everyday life means that you will not have any unexpected things going on. There won't be any surprises. You can plan successfully and take care of things exactly as they should be. But this seems to remove some of the elements of free will. If so, then this is something that we would have to confront and deal with. But time travel would have other benefits, and one of them is this. If we could send wormholes back in time, as I mentioned previously, and we could examine anything that happened in the past, then we could recover every lost species and species we've never even thought of before by directly reading the genome of living organisms. Species extinction would no longer be an issue because all of the information of our history would be available at our fingertips. Other things would occur as well. We would be able to get exact and perfect records of the climate over the previous years and have information to work from. We would have the ability to examine the solar cycle in great detail and predict exactly how the sun would act in times to come. Other unknown and unpredictable events in our future would become available to us as well, and we would have plenty of time to prepare for them. So time travel offers a lot more than simply being able to look into the past and look into the future. The information that can be gathered and, of course, transmitted would allow us to stabilize human activities and behavior over geological periods of time. But this sort of technology also comes with hazards. Imagine evil taking over the world and being unable to get rid of it because it would have a permanent means of reinforcing itself. Imagine a dictatorship so powerful and technically based that it would be unable to be displaced. At least in this time, with the unknown before us, we have the ability to resolve things according to our own struggles. But this also might be an illusion, because if wormhole time travel, as I mentioned previously, is possible and it's being done now, the past and the future are already connected, and I suspect that quantum mechanical effects would make the two agree with each other. The waveforms would match. You couldn't have paradoxes. So do we actually have free will? This is actually one of the toughest questions to resolve, but I think that we do have free will for the following reason. Suppose we knew that the future was fixed, and we couldn't make any decisions or choices or actions that would change it. We might not know what the outcome is, however, and we would still live our lives and make the same decisions the way that we would normally. However, we might choose to take an action, and that action be foiled or impossible for some reason, and that would result in the proper future. We still would have made the decisions we would have, meaning that we had the free will to make those decisions. Or does it? It's really impossible to say at this point. Time travel has other hazards as well. Let's imagine that we made a pair of wormholes and one was translated through time by traveling very rapidly, as discussed previously. Now you end up with one wormhole that is anchored in the present and another that's anchored in a different time. Essentially, entering the stay-at-home wormhole will take you into the future, and entering the other wormhole will take you into the past. Now, what happens if we bring those two wormholes next to each other, so that light falling in one exits from the other one? What would happen is very interesting. There is a physics concept called the Cauchy horizon, and this is an area where energy entering gets a frequency boost or an energy boost. Light, sound, matter, or anything entering the horizon becomes more energetic. And this is an area where it's possible for the energy to fall into the wormhole and exit again and keep re-entering and exiting again, gaining in intensity as it happens. What will happen with particles or matter falling into the Cauchy horizon is that it can induce an instability in the wormhole that ultimately makes it collapse or explode. Now, if we don't find a solution to the Cauchy horizon problem, it could be that wormhole time travel or wormhole travel in general could be impossible. On the other hand, there is an example in nature that shows that it might not be an issue, and that's called the Casimir effect. So we really don't know the answer to this yet, and it will take a lot of experimentation and mathematics to find it. But it's possible that wormhole travel might not work. Now, previously I mentioned negative energy and exotic matter as possible requirements for time travel. Those things are a little difficult for most people to understand, so let's have a look at what they are. All matter is made of energy, and all antimatter is also made of energy. When matter and antimatter, which is like its opposite or mirror image, collide, they annihilate each other and produce an extremely large amount of energy in the process. This is what Einstein was referring to with his famous equation when he refers to the idea that mass and energy are equivalent. A given amount of mass represents a certain large quantity of energy. Now, matter is made of energy, and antimatter also is made of energy. And when you put the two together, they essentially unwrap each other and become pure energy. But if we had an amount of raw energy and converted it into matter, we would get equal quantities of matter and antimatter in the process. Now, one of the great mysteries is at the creation of our universe, when it first began, there was for some reason a small excess of matter that we're familiar with, and not as much antimatter. Now, energy can be thought of as the catalyst for change. Without energy, there couldn't be any matter, and nothing would change. There'd be nothing present. So energy is the primordial stuff from which everything else is made. But this isn't true for negative energy. Negative energy would be to energy as matter is to antimatter. It's exact opposite. However, when energy and negative energy come together, what's left is nothing. In other words, they totally cancel each other out. Now, we know what energy is, but how do you get negative energy? As strange as it seems, people aren't exactly certain. However, there is something we know, and that's this. Energy is the source of all momentum, the force of movement. A photon, which is the basic particle of light and radio waves, is momentum, the force of movement. And when it strikes something, it carries that tiny packet of movement to the object that it strikes, whether it's an electron or whether it's an atom or whatever. Now, what's interesting is this. When two electrons are near each other, they repel each other. And they do this because of their electrical fields. And this is also a form of energy. But there is one force in nature that always attracts things, no matter what they are, and that's gravitation. And it does it in a very odd way. There's a theoretical particle called the graviton, the carrier of the gravitational force. And when it strikes an object, it doesn't push it away, it actually draws it toward itself, almost like negative momentum. In other words, gravitation acts like negative energy in this respect. Now, the theoretical physicist Robert Forward, who is also very good at working with gravity and its analogs, also had an idea that if you could use negative energy to create a form of matter similar to normal matter, it would be negative matter, and it would have interesting properties that are in many ways the exact opposite of what you would expect. One of those properties would be negative momentum. In other words, if you shoved it away from you, it would come toward you faster. And if you pushed it toward yourself, it would actually move away from you. Well, if we could create negative matter, this would be exactly the material we would need for opening a wormhole and keeping it open, because the harder the wormhole would try to squeeze it shut, the harder the negative matter would fight back to hold it open. That would be exotic matter. Now, exotic matter would have other strange properties. For instance, negative gravitation, and its electrical forces that were positive would attract each other, not repel, and its negative electrical forces would attract each other and not repel. But positive and negative charges would run away from each other. Exotic matter would have extremely weird properties, including the inability to form atoms as we conceive of them. It would also exhibit something known as negative mass. So when we talk about making time machines, we end up confronting things in physics that we're not even certain exist, or we'd be able to control if we could create them. Now, some actual experiments have been done using quantum mechanics and entangled photons. And it's interesting because the two different experiments in particular indicate different results. I mentioned earlier the grandfather paradox, where a time traveler goes back in time, kills his own grandfather, and therefore is never born. Therefore, he couldn't go back in time to kill his grandfather. So the question is, what really happens? In the 2009 experiment done by a researcher at MIT, Seth Lloyd, he tried to resolve the grandfather paradox using quantum teleportation and post-selection. And what happened was this.
In the experiment he did, there was no correlation between the person who entered the loop and the person who exited the loop. In other words, if somebody did go back and kill their grandfather, they would emerge in a different universe. And in the original universe, nobody would emerge, or somebody different might emerge. In other words, it's hard to say what would happen. It appears that the many worlds theory is true, and making such a choice would create a new cloned universe with differences. And that's the one that you would be in as a time traveler. Now, in a model proposed by theorist David Deutsch in 1991, his theory is paradoxes created by the closed time-like curves could be avoided at the quantum scale because the behavior of fundamental particles, which only follow the fuzzy rules of probability, would be the deciding factor. So University of Queensland physicist Tim Ralph decided to investigate Deutsch's model and see how it worked. He did the experiment with his PhD student Martin Ringbauer, and they led a team that experimentally simulated Deutsch's model of closed time-like curves for the very first time, testing and confirming many aspects of the 2-decade-old theory. Now, since they couldn't send an actual human being back in time, they simulated sending a photon back in time. And the photon had only a single job to do. It's to flip a switch. In fact, the switch that would create that photon. In other words, it would create itself by turning on a switch, thus proving that it was there to turn the switch on. What Deutsch's thought was to postulate self-consistency because of quantum mechanical effects. In other words, he insisted that any particle entering one end of the closed time-like curve had to be identical to the one exiting the other end of the curve. In other words, it had to be the same one. And the simplest way to do that was to say that at the creation of the photon, it had a 50% chance of actually achieving its goal. Now, what this meant was, when it was sent back, it had a 50-50 chance of hitting the switch and creating itself. And the photon that was created also had to have a 50-50 chance written into it. What they discovered is for the experiments to work, all that had to happen was everything had to have matching quantum probabilities. In other words, it had to assure its own outcome. Consistency was kept. But recent experiments have shown something much stranger than this. It turns out that quantum entanglement can actually reach into the past. By using quantum mechanical properties, it's possible to hook together photons that are already generated in such a way that things that happen in the future can affect what happened in the past. This is a counterintuitive result of an actual experiment. Furthermore, it shows that information from photons that are already created and then destroyed can actually be resurrected in the new entangled photons. In other words, giving us the ability to read things that happened in the past without actually having the information in hand. What this leads us to is the unbelievable ability to have an effect on things in the past, to read information that supposedly is already destroyed, and also to be able to do other things, such as break unbreakable codes. The properties of quantum mechanics are such that we can sometimes copy the properties of one particle onto another as long as we don't violate the rules. But in some cases, such as the closed time-like curve circumstances or time machine circumstance, we actually can create copies and then interrogate the copies and learn things from those copies without violating the rules of quantum mechanics. This is a soft form of time travel that actually allows us to retrieve hidden information. But will real time travel ever be invented? We're not exactly certain, but we do have some clues that would allow us to look for signs of time travel, or at least the retrieval of information from our time by other times. Again, we could look for small concentrations of mass or energy that are unexplained. These could be quantum wormholes used to carry information into the future. And we do know that quantum entanglement can in some cases allow us to affect things in the past and actually read information that normally would have been lost or hidden, already destroyed. So we're seeing some of the effects of potential time travel, but we don't really know if actual time travel exists. I do suspect that with quantum computing and better VR, we can get to the point where if we can retrieve information from the past, we can actually create simulations so realistic that we're able to interact with them and see what would happen if we had changed something, or if we were actually visiting a time in our history. My book recommendation is Black Holes and Time Warps by Kip Thorne, an amazing read, and it's online as a PDF as well. There will be a link on the page so that you can look it up yourself and read it at any time. Incidentally, Stephen Hawking threw a party for time travelers in 2009, and he didn't announce it until the day after the party, reasoning that they should have known if they were time travelers they could get there. Nobody knows if they were actually observed after all, though. This is Talk Universe. I'm Sir Charles Schultz.